Welcome back to this applied electricity session. This session isn't live, that is, we are solving the questions that were in the description link, the description of the previous video. Looking at the results, we realized that there are stuff we couldn't treat, and so scores were very low. We would solve all those ones and then continue from where we ended in the previous session. But before that, there's a message from our very own Naya Intodi to freshers in electrical and electronics engineering department, as well as all other engineering departments.
Hi everyone, my name is Nanaya Intudi. I'm a second year electrical engineering student. Now this YouTube channel is the ELEESA YouTube channel and you are welcome here. I believe that this YouTube channel is a very good initiative from the academic board of the ELEESA department. I urge you all to try and take the videos here very seriously. Watch and don't be selfish. Share to all your friends across the engineering department. Don't forget to turn on your post notification button so you're alerted anytime a video is out. And don't forget to like, subscribe, comment all your views, anything on your mind, just comment. And we are here to help you. Bye. Hi everyone. My name is
So, yes, that was a very short message to all our freshers, and we would love very much for you to subscribe, to comment, to like the video. So if you have any concerns, please comment. Our emails are our email is in the description of is in the about. You can find them in the description of the videos. Reach out to us if you also want to help in any way. If you want to recommend anything to us, we are open, and so do reach out to us. All right. So we had some questions, and we would like to go straight into those. And so we will answer the questions with our email while solving them here, so we see what actually we expected of each and every one of you. And so to our first question, we need to redraw it. We are being asked to calculate the effective resistance. Now we've learned how to find the effective resistance of components in series as well as components in parallel. And so that is exactly what we're going to do. Let's redraw the circuit. Um, yes, let's redraw the circuits. Um, all right. One resistor, another resistor, and another resistor. Another one this way. This. So that's quite a number of resistors. Okay, this should be fine. Okay, so we are to find the effective resistance between these terminals. That's our okay. So this is a 1 ohm resistor. I wouldn't add the units. 3.3. This is 4 ohm. This is 3 ohm. This is 6 ohm, and then this is 4 ohm. Now, we need to identify various components. Usually, what we do is to start solving from the farthest point from the terminal. So considering this, these are the terminals we are considering. So the farthest point from it is this end, right? This end. This is the farthest point. So now we now consider from here. So 6 ohm resistor. Is it in series or in parallel with any resistor close to it? We see a node here and we see a node here. It means it can be in parallel with this 6 ohm resistor. But how with this 4 ohm resistor, how do we find if they are in parallel? Like we said, take a path around it from 6 through 4 and back to 6. If it passes through only those two resistors, then they are in parallel, as we see here. So you see that the 6 ohm resistor is in parallel with the 4 ohm resistor. That's the notation for 6 parallel 4. You have 6 by 4 divided by 6 plus 4, which gives us 24 out of 10, which is equal to 2.4 ohms. So we can now draw the simplified circuit, which we will have as this. Let me change the symbols for resistors to make our work easier. This will now be represented by just one resistor. So this is A, B, this is still 1 ohm, this is still 3.3 ohm, this is still 4 ohm, this is 3 ohm. But then this is now a combination of 4 and 6. So this one goes away, we can represent it with just one resistor, whose value is now 2.4 ohm. So considering 2.4, we realize that this is not a node. But then in our drawing, we have brought it down just so we can have that closed circuit. So it could have been curved. So realize that over here, this is one branch. And since we have two resistors in the same branch, realize that 3 and then 2.4 are in series. That's 3 plus 2.4, which is what? 5.4 ohm. We can redraw a circuit and take this part off, come back to pick our pen and get our color, such that this is our new circuit. And then this will change its value to 5.4, as we have seen, right? 5.4 ohm. And oof, sorry for that. Back off. Okay. So realize that now 5.4 ohm. Moving from here, we can pass through this 4 ohm and then end here, realizing that 5.4 is in series with 4. What we now have is 5.4 in series with 4, which is 5.4 times 4 over 5.4 times 4. We enter into our calculator, gives us 8. Sorry, this here is a plus. This here is a plus. This right here is a plus. and the result is 2.298 ohms. We need to redraw our circuit. We'll let me make this larger since we have this here. So, good. Okay. So making our space better, so we have more space to do that. Okay. So we are redrawing our circuit. Black. So we now have the circuits this way. Have this, have distance here, and have A, B, and this is our red color for our values, which is still 1, 3.3, and then this is now 2.298, which is in series with 1. We realize that we now have 1 plus 2.298 is 3.298 ohm. And so finally, our simplified circuit is something of this sort. And then we have this here. Well, this is 3.3, this is 3.298. And you realize that A and B can move from this through this without passing through any other element. So they are in parallel. So we know that 3.3, 3.298, which is equal to 3.3 by 3.298 divided by 3.3 plus 3.298. We are punching that into our calculator and then we'll show the results very soon. And the result is 1.65 ohm. So that is the result of the calculation. So we see 1.65 ohm here and pick it. Next question. So I hope this is understood. Okay, so to our next question. So we are being asked to determine the supply current in the circuit below. And if you remember, in the previous video, I mentioned that the supply current is determined by the effective resistance of the circuit in which the voltage source is in. And so the supply current is dependent on the effective resistance. So we need to now find the effective resistance here. And the effective resistance will now allow us to find the the supply current. So let's consider the circuit. All right. So we have a 4 ohm resistor, a 3 ohm resistor, a 5 volts battery, and then a 2 ohm resistor. Now, in simplifying the circuit, realize that I said we try as much as possible to start from the far end. But in this case, we are going to consider something. Remember, we did something on short circuits, right? When current flows from this battery till this end, there are one, two, three branches for current to flow through. And I said current uses the path of least resistance. When current should use this path, there's a resistance. When current uses this path, there's a resistance. But if current should use this path, there's no resistance. And we say once there's a path of zero resistance, all the current entering the particular uses that path. Okay? Wouldn't branch here, wouldn't branch here, but then will all flow through the side. What it means is that we have short circuited this portion as well as this portion of the circuit. And so our simplified circuit is now this. The 5 volts battery and then our 3 ohm resistor. So the supply current I is equal to V over R, which is 5 out of 3. This gives us 1.67, right? 1.6 recurring, 1.6 recurring. So we can see 1.67 amperes. And very easily we have solved our question. Answer. And on to the next. You realize that's very simple. Once you're able to identify that this here, this part right here is a short circuit. And when we say it's a short circuit, it means that it takes other parts of the circuit out of the circuit. So it means that this circuit, this branch will have zero current flowing through it. So we don't consider it when considering the effective resistance. Same applies to this, right? So we have a very easy circuit to deal with. And then this is our current. The second question was very. For our next question, we want to move to solve the next question. It is saying that find the equivalent resistance of the circuits below. The unit can be either the symbol or the unit in words. Note that your answer should be two decimal places. That means after you solve this, you should leave your answer to two decimal places. It is important to know that even as we are trying to help you understand the various concepts, we want you to also take notice of some of the things you would be seeing in your exams, which is the the specifications of how you should present your answer, right? Good. So it says two decimal places. So as you are solving, we should remind ourselves of that. Changing color to draw the circuit. Have voltage source, the resistor, uh, this, and that is it. in this, back to my pen, we have this and that, and this. So this is a V. We have a 3 ohm resistor, 2 ohm resistor, 6 ohm resistor, and then 4 ohm resistor. So just like in the previous one, we can now easily identify that the 4 ohm and then the 6 ohm resistors are parallel connected. So that's a 6 parallel 4. Now 6 by 4 over 6 plus 4, which equals 2.4 ohm. So we can now draw a simplified circuit, right? This still here, and then this still here. This now becomes just 1, whose value is now 2.4. Then this value is 2 ohm. Then this is 3 ohm. 3. Quite easily, we identify that 2 ohm and then 2.4 ohm are in series. We say 2 plus 2.4 equals 4.4. We can now draw an equivalent circuit to have B 3 ohm and then this right here. So this is 4. So this is now 4.4 ohm, as we've seen, 4.4 ohms, and then 3 ohms. And as we can see, they are parallel connected. So the effective resistance of this circuit is now 3 parallel 4.4 equal to 3 times 4.4 over 3 plus 4.4. Then that into a calculator gives us 1.784. I said we should leave it in 2 decimal places, so we have 1.78 ohms. We can redraw the simplified circuit, which will look something like this. With this here being 1.78 ohms. So we do that here, 1.78 ohms. So we move to our next question, which is on current division, which we didn't treat in the previous video. However, we'll go through it. The today's live stream fortunately hasn't been uploaded, and so after it is done, you will understand it better, and then you would understand the solution better. So draw the circuit. Since you are seeing it, can you follow this? Such that okay. So what we realize from here is that this 2 ohm is parallel connected to this 2 ohm and is parallel connected to this 2 ohm. And we identified that for a certain, what we'll do here is to find the effective of these two so that we now have just two paths for current to flow through. Realize that 2 parallel 2 is 2 by 2 out of 2 plus 2 is 4 out of 4, 1. So we have a new circuit with 1 ohm, 3 ohms, and then 12 volts. Since we want to find the current here, which is I1, we can only find if we know the supply current from the voltage source. But we learned that the supply current from a voltage source is dependent on the effective resistance of the circuit. So now let's find the parallel connection of these two. And then that will be our effective resistance, and divide 12 by that. So that is 3 parallel 1, which is 3 by 1 divided by 3 plus 1. 3 out of 4, 0.75 ohms. So it means that if we have a supply current I is going to be equal to 12 volts over 0.75 ohms, which is equal to 16 ampere. Now, if our supply current is 16 ampere, how do we find the current here? As we'll learn in current division, it is dependent on the resistance in the other branch, which is the effective resistance of these two, will determine how much current will flow through the 3 ohm resistor. So we have I1 to be equal to the effective resistance of these two, which we've drawn here to be 1, out of the sum of these two, 1 plus 3, times the total supply current, which is 16 amps. That is 1 out of 4 times 16, which is 4 ampere. We'll now input our answer as 4 amps. And so finally, our last question. I want to find the value of I in the circuit. Now I want us to observe something. The current flows from this source. When it gets here, it sees a resistance part here, a resistance part here, a resistance part here, a resistance part here, a resistance part here. So it splits into this part and then this part. And when current gets here, there's a resistance part here and a resistance part here. So it splits again. But when current gets to this particular node, there's a part of zero resistance here, and then there's a resistive part here and a resistive part here. And so when it gets to this node, there's no split of current. All the current passes through this. Realize that this entire section of the circuit is cut off, and we wouldn't need it. And so an equivalent circuit for this is what I'm coming to draw, because this side has been cut off. So we go through that. And but by the way, you are finding I, so let's not forget about that. And there, this is 4 ohms. This is I. This is 25 volts, 1 ohm. This is 2 ohms, and this is 3 ohms. That's the 2 ohms and then 3 ohms are parallel connected. And also see that 2 ohms and 4 ohms are parallel connected, and then 4 ohms and then 3 ohms are parallel connected. We can pick any of them in any order and then solve them. We can pick 2 and 3 in parallel first, and then pick 3 and 2 in parallel in whatever order we wish, right? I will do it this way because we have I here. So 3 parallel 2, 3 by 2 over 3 plus 2. That leaves us with 6 out of 5, 1.2. Write that out. So we simplify the circuit. We can now convert this to a simplified circuit. I would rather prefer to clean. So, um, that will be it. Now take away this portion, then because that is the effective, this value is now 6 out of 5 or 1.4. Now realize